Let's have a look where we are. Gabversity, where facts don't care about your feelings. Let's see what's going on. Looks like we got everyone here. Looks like that's the table. All right, so D. Javier, welcome back, my friend. All right, so we're going to talk about galactic evolution and formation. Now later on, we're going to get into distance, the Hubble law, which is the expansion of space itself. Hello, supermassive black holes, dark matter, gravitational lensing and dark matter, and what else? We're going to talk about how many galaxies there are, etc., etc. Let's see if I can get a better shot of this. See if I can talk to you guys. I don't know if that's actually better or not. It's probably worse. Let me go back all the way here. Alrighty, good to see everybody. Alrighty, so let's begin. Now we can talk about the Milky Way and almost everything we see. We spoke about this yesterday, just to recap, right? So almost everything we see in the night sky belongs to the Milky Way. Hey, Cyanide, hello, everyone's here. I can barely see from this the screen, what's going on, but I'll do my best. The Milky Way from the outside looks like a Snickers bar. It does not. It actually looks like a disc. Hey, where are you today? Hello from, I can't see the flag. From Jamaica. Welcome back. All right, so first studies of the galaxy. So up until, as I was saying before, our grandparents, right? Like my grandmother was born during the Second World War, right? And they, up until then, still thought the Milky Way was freaking, I don't know, what do you call it? They thought that was the whole universe. So talk about whatever the hell is going on there. Anyway, so then it turns out that there was stuff that were not in our universe. So, you know, like the Crab Nebula, which was a supernova. And the supernova exploded in 1054, which happens to be the same year of the East-West schism of the of the church in Europe. I don't know. Talk about two supernovae in one go. All right, so and we're feeling the effects of both even till today. I thought that was quite funny. All right, so the structure of the Milky Way, we got the galactic plane, the galactic center. So it shows you, right, how crazy are we as humans in the sense that we can't even see anything, right? And I mean that metaphorically and literally. We had to use infrared and radio to be able to see into the center of the Milky Way. Before that, we couldn't see anything. So we got globular clusters, dense clusters, and they're very old stars, which is why they're so dense. Where are you? How come you have sun? I stole it from you guys. I am down under, buddy. Here you go. So this wife beater shirt, I think it's got roughed up from all the wife beating. So the globular clusters are really old. Now, if you think about it, that just sounds like, oh yeah, they're old. Well, how can a globular cluster be old? How can it be old? If there's a group of old people, right, then, sorry, let me rephrase. If there's a group of people and that group has been around for like 60 years, well, then clearly the people in the group must be older than 60 at least, right? Otherwise, how could they be there if the group has not changed? And that's why globular clusters look red, because they're old stars, and the old stars burn slowly. They're like, easy going, son, easy love, right? You know, the large stars that like burn all their gas, they burn out immediately. They're like young people who party hard and they're gone, right? But these ones just plod along. They don't party much. They hang out, and so they last so much longer. All right, structure of the Milky Way. We've got the disk, which is spiraling. We've got the arms, okay? And obviously, you guys know that. Locating the center of the Milky Way, that was not easy. And it took them decades. You know, the people who started looking for it didn't even find it until God knows when. All right, so I might try and hold this phone upwards because this is bothering me. Let me just get this wood, sorry. Let's see what we can do. Why am I upside down? Why am I upside down? Bloody hell. What have I done? Can't win. I don't know what I've done. There we go. Now I'm back to normal. All right, cool. So, structure of the Milky Way. Okay, strategies to explore the structure. So number one, stars are rich in refried beans. Hey. Observe objects at wavelengths other than visible. So that's one of the things, right? So we had to go into space and actually look at X-rays, gamma rays, etc. that were blocked by our atmosphere. On top of that, we had to look at infrared, because infrared is like this long, hey, just relaxed, and it pierces through everything. The problem with astronomy is that everything is a dirty joke. It's one of the problems I have with it. That's probably why I can never be an astronomer. I'll just be laughing my ass off. All right, exploring the galaxy using clusters of stars. So you can look for the globular clusters because the older ones are obviously evidence of what has been around the longest. All right, not like so you look for the nursing homes, basically. The globular clusters, as I said, there are about 200 globular clusters in the Milky Way. We are all dirty-minded, especially on Friday nights. Right. What's interesting is that there are 200 globular clusters. These are the really old ones, and each one has up to 1 million stars. So 200 million stars. Now we know that almost every star we've ever seen, like us as humans, has now a planet attached. So if you think that there's 200 million old stars, how many planets are there, right? And how many of them do you think don't have bacteria on them? No one knows, but it's just a phenomenon. We're going to get into that I think in the next couple of chapters. We're going to talk about extraterrestrial life, the chances of it, mathematically speaking, statistically. All right. So it turns out, as we discovered more and more of the universe, that of course banter is fun. That's what we discovered. But we discovered that, oh, hold on, everything is not rotating around our sun. So first we thought it was around us on Earth. Then we're like, oh no, actually it's around the sun. Now it's actually, we're not even nothing. We're a nothing. We're in a suburb right out the edge somewhere. It is a beautiful Aussie day. Their bacteria is detected the same as ours. That's true. That is also true. We will get to that, but yes. That one's going to be a good scope, I can tell already. Okay. So all of these clusters were centered around something we couldn't see, this mysterious thing hidden behind clouds. So we had to develop as humans technology to see infrared and radio. Tweeted me? Awesome, thank you. I will look at that. Structure of the Milky Way. We've got the nuclear bulge. Hey, got the bulge at the center. And then we've got the halo, and we've got the globs on the side. All right, so that is the structure. All right, infrared view. This was in yesterday's lecture. That's why I'm going a bit faster. Infrared view of the Milky Way. By the way, on the Pompous store, I have some Gabversity products now. I have a Gabversity mug, Gabversity pens, Facts Don't Care About Your Feelings, Irrational t-shirt. That's at facebook.com/gabsmacked. Infrared view of the Milky Way, massive stars and open clusters. All right, the infrared view is pretty good. Bulges in globular clusters. Damn straight, Captain Deltron. All right, and it was great. See, humans can't see infrared, but it doesn't make infrared less important just because we're blind to it. Right? Well, we sense it through heat, but clearly, computerized technology can modulate those waves and squeeze them upwards into the visible spectrum. So it's a mathematical representation of what they would look like if they were in visible light. And using that, you can see the nuclear bulge right at the center. And I'm going to show you the bulge, my friends. I showed this yesterday, but I will show it again. Here. No, can't see what I'm doing. Hold on. I'm going to flip this camera around. My man, Sunagon, welcome back. So, I don't even know. Yeah, there we go. So, you can see there and here, that's the Milky Way in infrared, and there you can see the bulge in the center and the galactic plane. So, everything's sort of around that plane rotating. By the way, I've opened a critique of the book called Real Speaking Human. I think it's at facebook.com/Real Speaking Human. Because it turns out that the book is actually, I didn't realize this, but it's a collection of short stories which are loosely related, all about the autistic savant. And they have a common theme, but it's not one continuous story, now that I look back at it. The other thing is that the girl who wrote the book used a ghostwriter. The ghostwriter is me. So I ghostwrite a story from a girl about me, if that makes any sense. So it's a bit confusing. All right, exploring the Milky Way with massive stars and open clusters. All right, we've gone through that before, right? So massive stars are an easy way, of course, because they're so massive and bright, we can see them. But the problem is that they burn out quickly, right? They're like a mad-ass V8 engine, right? And it just burns all its fuel. So they're hard to find. Massive stars and open clusters, right? So open clusters are the most luminous, of course, because they're young and do not belong to the association. Members that have together move side direction. Okay, a view of galaxies similar to our Milky Way. So we can see like the Sombrero galaxy. See, I'm surprised no one wants to change the name of that. It's called the Sombrero galaxy. And you know why it's called the Sombrero? I'll show you. Look at that. That is called the Sombrero Galaxy. Alright, and as dark clouds, and right there. So you can see that we've got dark and bright clouds. Now I'm pretty sure the dark ones are before stars ignite, so that must be where they're being created, I'm thinking. Now I'm not sure on that, we'll have to wait and see. Disk stars. So there are two types of stars. There are disk stars and halo stars. Okay? So disk stars are the ones that orbit the center of the galaxy. Halo stars, Kevro, hello. Halo stars are the ones that sort of orbit in any direction. So they don't always follow the galaxy. They can go this way, they can go that way, and they make a halo. So there's like a 3D soft halo, hey, around the galaxy. And that halo are those random stars that prefer to go their own way. You can go your own way. All right. Orbital motion. The sun, our sun, orbits the galaxy at 240 kilometers per second. True faith. Fleetwood, you know, yeah. All right, so it's about 100, what is that, 180, would you say? 180 miles per second? 180. So one's a 668, 40. 190. I don't know what I'm doing. 1.62. No, it wouldn't be that high. 150, which is 70. Yeah, probably 150 miles per second, something like that. Stars closer to the galactic center orbit faster. Well, you would expect that, right? Stars further out orbit more slowly. And that suggests to me anyway, that the stars formed within the galaxy. Because they are traveling at the speed that you would expect of a galaxy that was made of dust. Because when you hold your arms out, right, and you're spinning around, of course the inside are spinning. Hold on a sec. Yeah, if these ones came in, right, your hands have to spin faster for angular momentum conservation. So I don't know. That one, I don't know. I'm just speculating. I have to wait and see what they say. All right, so next, finding mass from orbital velocity. That one's really good. So what's interesting is that the orbital velocity, if we know the speed of these stars rotating, we stardust harvesting star stuff. Yes, very true. Very true. We can actually find out the mass. So yeah, the more mass there is inside the orbit, the faster the orbit has to go. So we found graphing, isn't that what Carl Sagan said? Something like that from memory. I'm not the best on Carl Sagan, but it definitely sounds right. Total mass in the Milky Way. The lower limit is 400 billion solar masses, right? If you add the halo, as we said, the halo goes around the Milky Way. So the Milky Way is not just the disk. There's also a halo that goes this way because there's lots of other stars that sort of go their own way. All right? So 1 trillion solar masses. Now, what's interesting is that almost all of the mass is not detectable at all. So what is that? No one knows. No one knows what this mass is. There is a mass, most of the mass in the frickin' galaxy is stuff that we don't even know what it is. It's not on any of the atomic, it's none of the atoms on the frickin' atomic chart at all. We don't know. It's some random matter. So we call it dark matter. No one knows what the hell it is, right? So they're trying to detect it, which is quite fascinating. And without that dark matter, the galaxy would have blown apart ages ago. So it's a very interesting phenomenon. Tracing, we'll talk more about dark matter as we get along in the series. Tracing spiral lines with OMB associations. So near the sun, we get OMB associations determined using Cepheid variables. All right. Blown or ripped apart? Probably ripped and blown. Hey. Radio view of the Milky Way galaxy. This is one of the best things. You know what's crazy about like radio waves? If you think about this, light waves are so short. They're like, you're talking billions of a meter, right? Like 6 billionths of a meter or 60 billionths of a meter. Radio waves are 21 centimeters, right? Which is like a fifth of a meter. Think of how long a radio wave is. So it's not going to get, it's so long that it doesn't get interrupted by particles because it's so freaking long, it just passes right through them. So using radio waves, and then we squeeze them down to look at them visibly, we can see what's going on with the Milky Way. Now, why is this beautiful? It's beautiful because we're using all these different sensors and we're getting the same type of images, which shows us that what we're looking at is probably real, or real enough, I guess. All right, so have a look at this. Hey, Abyss. So this is the radio wave version, sunny side up, of the Milky Way. So it's fantastic, because without that, hey my friend, without that we would never be able to see what's through the Milky Way, because we're blinded by all of the dust that just blocks our view, because we live way out in the country. I guess in our solar system is right out in the country, right? We're like, hey man, how you doing, son? And then the rest of the freaking galaxy is in the city in New York. So imagine trying to use a telescope from, I don't know, like the most obscure country town somewhere in Texas, and you're trying to look at freaking New York, right? And you got cars flying everywhere. You're trying to look into like the Empire State Building, or I don't know. Sorry, I don't know my buildings very well, but construction. So the center of our galaxy is all construction. So how do they do it? Well, they look through it. They look right through it by using radio waves. I love that. Love that stuff. All right, radio observations. So radio observations also reveal the distribution of hydrogen, neutral hydrogen, right? And what's interesting is that the hydrogen is concentrated in spiral arms, and so you can track it, so you can figure out how fast the arms are spinning. Isn't it amazing what we little frickin', advanced apes have been able to do? I love that stuff. All right, let me just turn the page. Tracing molecular clouds. All right, let's go. Molecular clouds, okay? So for example, the CO molecule can be used to trace the distribution of molecular clouds. In some directions, many molecular clouds overlap. Clouds can be disentangled using velocity information. So mathematically, you can extract the wave equations, which is the velocity of each of these clouds, and then you can figure out that actually it's two clouds crossing each other. I tell you what that is like. Imagine we're back in this country town somewhere in the South of America, right? And it's called Lasso, right? That's from Kingsman Statesman or whatever, a Golden Circle. So anyway, you imagine looking at New York and you see two cars going past each other, or they're sort of merging or going the other way. Yeah. You can't tell if that's two cars or if it's one car, right? So you can't tell. Tommy Watkins, long time. You can't tell if the cars are crisscrossing or whether the cars are rebounding off each other and going their separate ways. You can't tell, but because they have different speeds, you can mathematically disentangle that. I demand, auntie. Hello, love. I was talking to one of my mum's friends just now, because she talks like Auntie May. So, and I said Auntie May's a real hit with gay guys, and she said, oh, probably because she sounds like Dame Edna. Scopes and work on your southern accent, hun. I have to. Oh, I didn't even know you had scopes. Oh my god, you got to tweet me one to Gabversity. I'm definitely gonna watch it. So yeah, I want to learn how to mimic that accent. It's called a lasso. So I said to her, "Hello, I'm Auntie May," and then she says back to me in the exact same voice, "Hello, love," because that's her voice. Distribution of stars and neutral hydrogen. All right, distribution of dust. Okay, so let's just to show you southern from the community. All right, I love that southern accent. By the way, I love that southern accent. It's freaking hot as. I don't know why. I think maybe because I'm not an American. If I was there, maybe I wouldn't like it. So I'll show you where the sun is, right? Just to give you an idea of like how distant we are from everything. All right, have a look. So the sun is way out there, and that's inside the Milky Way. So we're a nothing of a nothing, basically, which is pretty damn awesome. Otherwise, we wouldn't have been able to function. Auntie May, love. Tommy. Is Tommy still here? I've got to ask him a question. Let's see if he's still here. I think he's gone. That's a shame. Yeah, I was gonna tell you, Tommy. I've got an offensive one with Auntie May, like really really offensive. It was on a private channel, and she just lost her mind. So I thought, if you want, I'll send that to you via a private link. I'll tweet it out on Gabversity or something. But it's really offensive. Star formation in spiral arms. Shock waves form from supernovae ionization fronts initiated by the O and B stars. And the shock fronts forming spiral arms trigger star formation. And all that you see was created by the flying spaghetti monster. Damn straight. He flew past and let there be flying spaghetti. Spiral arms are stationary shock waves called spiral density waves initiating star formation. Alright, gotcha. I love when Auntie May gets crazy. That's right, you got to see it. Yeah. Are you in the Unsmack channel? I had to delete it because I don't know why, man. People share shit with the groups. Whenever I make a group, someone just shares like radical shit with me, man. And I'm like, man, we're trying to like just have some fun. I deleted it anyway. Alright, so star formation in spiral arms. Alright, so a spiral arm of the galaxy. It sort of looks like tentacles, right? Our galaxy. They are stationary shock waves. Alright? So try and understand that one. It's a shock wave that doesn't move. Right? But the stars and the clouds orbit around the galaxy and pass through the shock waves. So we pass through in and out of shock waves, right? The shocks are like ignition, like the starter motor of a car. It's like pumping electricity through fuel and igniting it. That's what happens, right? The gas clouds, this wave passes right through them. And as it passes through, the star becomes alive and it ignites it. And when the star ignites, it blasts all with its solar wind, all of the crap outside, and then forms a solar system. Happens. It's just I think it would be awesome. Our ancestors one day could be able to watch that. How awesome would that be? Shocks initiate star formation. Star formation self-sustaining through O and B ionization fronts and supernova shock waves. So they're self-sustaining because of the ionization fronts by the O and B stars. Because those stars are so powerful that they just rip apart atoms and they make them like either positive or negatively charged. And that magnetization and can continue the... Who do we got here? Jeremy Jenner. Hey, Jeremy Jenner. That's funny. The nature of spiral arms. They appear bright, invisible light from newly... So when these stars ignite, and they're gigantic, they're like, you're talking thousands of times bigger than our sun, right? And they are all getting ignited in those shock waves. So as they're getting ignited, everything's lighting up. So if you zoom out of, say, above a national park, wherever you see campsites, you're going to see fires. So those fires will make like a pattern in the national park, because that's where all the campfires are, right? So sort of like that, I guess. Grand design spiral galaxies. All right, the grand design spiral galaxies, okay, they have spirals, have two dominant spiral arms. So it's like two arms on either side, right? And then they just wrap around, which is pretty awesome. And then you have woolly galaxies, which their real name is flocculent. Hey. Would you like some flocculent? It's also woolly. They also have spiral patterns, but no dominant pair of spiral arms. So they're sort of like a bit more of a blurry spiral galaxy, which is good to know. Each one tells us something. All right, self-sustained star formation in spiral arms. So here are the steps that we spoke about, right? We have, it's self-sustaining due to ionization fronts and supernova shocks. So those shocks just blowing crap into submission. Okay, so it's pretty awesome. Right? And as they pass through, at least they're not flatulent. Yes, I'd go flocculent first. It's a good one. The whirlpool galaxy, right? M51 is a whirlpool, as if they are being stirred by a giant spoon. Yeah, that's a good one. I like that one. The spaghetti monster spoon. All right, so self-sustaining star-forming regions along spiral arm patterns are clearly visible. This is crazy to look at. This is ignition time, right? Have a look at this. Right here. So ignition time. You can see all of the red. That's all stars just being born, just igniting up like all the campfires. That's just crazy. The galactic center. Okay, our view towards it, we can't see anything because of the gas and the dust. All right. Extinction, only 1 out of 10 to the 12 optical photons makes its way from the GC towards Earth. So 1 out of a trillion. 1 out of a trillion optical photons makes it to us because all the rest get blocked. So we can't see anything. And it just looks like you're looking at dust. You can barely see what's going on. The radio view, right, shows us that there is a supermassive black hole at the center of our galaxy. And have a guess how many times bigger than our sun the supermassive black hole is. Who would like to have a guess? I have a feeling Abyss already knows the answer. Probably a few other people. And time is ticking. It is 4 million suns. 4,100,000. Oh wow. Well, if something can surprise Abyss, then that's a big surprise. Close. Yeah, I didn't actually know this either. It was 4 million solar masses. 4 million, right? And it's compressed into a black hole, so it's probably not that much, not very big. All right. Now what's going on is, how did they find it? It's bonkers, right? I know, it's ridiculous. How did they find it? Well, they tracked all these stars, and what was going on was the stars were orbiting what looked like nothing, and they were coming close, and like the stars were going like hundreds of thousands of miles a second, like flying around this thing. They're like, what the hell could be? It's so small. What could have that much gravity? And they realized, holy crap, Einstein was right. We found our black hole. So that was what was going on. Anyway, so it turns out the neutron star and black hole binaries are circling each other, and the neutron star is getting ripped to shreds, getting sucked into the black hole as they orbit each other like crazy, right? Supermassive black hole in the galactic center unusually faint in X-rays compared to those in other galaxies. Okay, metals in stars. Metals in stars. Here we go. Absorption lines almost exclusively from hydrogen. Now what's great is that because we live in a pixelated universe, as we talk about in quantum mechanics, Sagittarius A is supermassive black hole in the Milky Way. That is exactly correct. In fact, I was exactly talking about that too. That's exactly right. All right, so the Milky Way at its birth was only hydrogen. Now, how do we even know this stuff? Well, firstly, we live in a pixelated universe. Because we live in a pixelated universe, when we receive the light, it comes in certain pixel sizes. And based upon the pixel sizes and the gaps between pixels, we know what metal is reflecting, or what atom is reflecting that light. Isn't that crazy? It's like, I don't know. I just find that crazy. Anyway, so, and in quantum mechanics, I explain why that happens. But anyway, basically, it turns out that everything was hydrogen and then helium. And then over time, with the bigger stars, when they were dying and fusing, from their CNO fusion as well as their supernovae, they would create everything heavier than iron. All right. Young stars in the stellar populations are metal rich, and they're in the spiral arms and the disk. The old stars are metal poor, and they're located in the halo and globular clusters and nuclear bulge. Old stuff's in the bulge, my friends. All right, the abundance of elements in the universe. All right, basically, hydrogen basically represents 999,999,999,999 atoms for every 1 trillion. Basically, for everything else. So, which is really funny because all laws work like that. It's called the Pareto distribution. It's hilarious. So yeah, basically everything is hydrogen. Heavy metals might have been created when white dwarfs collide. Interesting. That would make sense, because when they collide, their mass exceeds the allowable mass for a white dwarf, and then the surface explodes in a nova. So that absolutely, yeah, that would make sense, yeah. So galactic fountains, hey, champagne showers. All right, so multiple supernovae in regions of recent star formation produce bubbles of very hot gas. Hot gas can break out of the galactic disk and produce a galactic fountain, which shoots right out into space. Quantum John. As the gas cools, it falls back to the disk, spreading, it spreads its heavy elements throughout the galaxy. That is so cool. So it's a galactic squirt, and it squirts everything all around the galaxy, which creates new planets, new stars, and able to sustain life. Amazing how all of this works together, huh? All right, the traditional theory of the galaxy formation is that you just have hydrogen in a cloud, and then this gas turns into smaller pieces which coalesce into stars within this cloud. And then as the cloud's rotating, it rotates into a disk. And then as the first clouds die, we are the gibs of star stuff. That's right. That's so funny. And then as the first stars that come out are like massive, right? And then they die quickly, and as they die, they produce the smaller stars, which are the Series 2 second generation stars, like our stars, right? And those ones already have metallic atoms in them, and that's how we can have carbon and water and all these other things. All right. Now, there are some changes to this theory. Changes are this. Later accumulation of gas, probably due to mergers with smaller galaxies. So there were probably smaller galaxies as well that merged, became part of the family through immigration, right? And changed the galaxy and made it richer and more diverse. Too funny. Recently discovered rings of stars around the Milky Way may be the remnant of such mergers. So they've recently discovered those, so that could be the case. All right. This is our last note. Yeah, this is our last note, and then we'll stop here, and then we'll have another lecture later on. McDuda always comes at the end. Always comes last. He's probably a really good partner. Yeah. Too funny. All right. Oh, by the way, is your second beautiful child, second beautiful child born yet? We're waiting, man. You gotta populate the West with more beautiful white, brown, Korean mix of truck driving 10 weeks. All right, man. Keep us posted. Make sure you tweet to Gabsmack. We want to see some photos, man. The bottom-up hypothesis. All right, the bottom-up hypothesis. Hey. Smaller star systems accumulated to form larger ones, which led to the formation of the Milky Way. So that's another option, right? Anyway, so we will talk about galaxy classifications in the next lecture. And that's it. For now, I'm going to go back and do some mathematics on my own for some fun. And I got some projects to write up for uni. So I will leave you all. My granddaughter turned 3 today. Oh, no way. Her little sis is late. Oh, she was due yesterday. Oh, Carol, you got to let us know. Tweet us at Gabversity. We know what's going on. Oh, that's awesome. All right. Well, congratulations. Facts don't care about our feelings. Remember at Gabversity. And later on, we'll be doing languages. And we'll be doing history, and you're gonna love those ones. All right, guys, love you all, man. Don't forget, become a Patreon member, and we will grow this bugger. Good morning, good afternoon, good night. Love you all, man.